In the previous module, you learned about segmentation as one of the techniques in non-contiguous allocation. The second technique under non-contiguous allocation is paging. Recall that in memory management with segmentation, the size of each segment varies. This is why the segment table must include the size or limit column. Each segment corresponds to one logical unit in your process image, like code section, data section, and so on. If you have a large amount of data, the resulting data segment will be large. Memory management with paging deviates from this design. The MMU hardware with paging enforces all segments, quote-unquote, be the same size. Using uniform size segments, the segment table does not have to store the segment size. It only needs to store the start address of each segment. Let's look at the design consequence of uniform segment size to the segment table. The illustration here assumes that the MMU hardware uses a segment size of 2000. Be aware that this is not a real example. We use 2000 just to make our explanation easier. Real MMU's hardware will use segment size, which is a power of 2. So instead of 2000, a real MMU would use 2048. The leftmost table shows a hypothetical segment table when uniform segment size is used. The limit column shows all 2000. Therefore, it is useless to store the size in the segment table, and the segment table now stores only the starting address of each segment. Also notice that when we use uniform size of 2000, all segments must begin at an address multiple of 2000. So, for instance, it is impossible to have a segment that begins at address 7000 because 7000 is not a multiple of 2000. But this observation leads to another simplification. It is not necessary to keep the full address that requires more bits to store. By dividing each number, these numbers, by 2000, the segment base address can be stored using fewer bits. So by dividing these numbers with 2000, what we get is now 3, 0, 6, and 4, and these smaller numbers will require fewer bits to store. So now these numbers refer to the page number. So this number is not the beginning address of each segment, but these numbers are now what we call the page number. So we are transitioning from segment table into a page table. And likewise, in segmentation, we have to have a register to store the starting address of our table. That register is known as segment table base register. When we are using paging, we need to use the same register, but this register is not properly called page table base register. In segmentation, the CPU will issue the logical address as a pair of segment number and offset. Now, when paging is used, the CPU will issue the address as a pair of page number and offset. So let's look at another related issue of fixing the page size to some value like 2000 in our example. Now consider a process whose code size is 9000 bytes. Of course, the code will not fit into one page, and instead 5 pages are needed. But out of the 5 pages, the last page occupies only 1000. So we see the same issue of internal fragmentation as we have seen in fixed size partitioning before. But what is the benefit of paging? In segmentation, the operating system must look for one contiguous memory of size 9000, but now with paging, it is easier for the operating system because instead of looking for one contiguous 9000, it will be looking for 5 separate areas of 5000 each. Before we look at the details at paging implementation, let's understand that paging mechanism can simplify the design of MMU hardware. The illustration on this page shows a process whose overall logical layout requires 10 contiguous logical pages. To make the explanation easier, let's use again unrealistic page size of 1000. So that's why you see the first page begins at logical address 0, the next page begins at logical address 1000, and so on and so forth. So let's say the code requires 2300 bytes, and the code occupies the first 3 pages, the first 3 logical pages. And then let's say the data is 1200 bytes. That will require 2 contiguous logical pages. But remember that each page cannot be shared by 2 different contents, so the data has to start at a new page boundary. So for this example, the data of the process has to start at logical address 3000. And let's look at the heap, and then let's say the heap is 2500. It will require 3 pages, and let's say the stack is 1300. That will require 2 logical pages. So remember that in segmentation, the segments of a process may not be placed contiguously from each other in RAM, but also recall that each cohesive block itself, code, data, heap, and stack, is stored contiguously. With paging takes this idea to the next level. Each cohesive block itself does not have to be stored contiguously in RAM. As you can see from this diagram, I'm using the same color boxes, green for code, and then orange for data, and so on. So in the RAM, it is possible that the 3 pages of code are not stored contiguously. The first page of code is at address 11,000, the second page of code is at address 3000, and the third page of code is at address 0. So the code sections itself are not contiguous. Same thing for the data. Data is not contiguous, and the heap and the stack. By the way, to remove clutter, I don't include the heap in my layout. Now to disambiguate logical layout, which is always contiguous, versus the physical layout, which is not contiguous, we will use the word page to refer to areas in the logical space, and we will use the word frame when we are referring to areas in the physical RAM. So this diagram shows you 10 pages, 10 contiguous pages of a process, and we have 13 frames in the RAM, and out of 13, 10 of them are used by our process. So now somehow we need to tell the hardware how to find our frames. This is when the numbers in the page table becomes important. So what does this page table tell us? So in our logical space, we have 10 pages for our process. That's why you see 10 entries in our page table. So the number of entries in our page table is always the same as the number of pages used by our process. And out of the 10 entries in our page table, the first 3 entries correspond to the code because the first 3 pages are our code, and the next 2 pages are our data, and that's why index 3 and index 4 will be used for the data pages. And the number inside the page table will tell us where to find each frame or each page. So here, page 0 of our code can be found in frame number 11. So code 0 corresponds to the first page of code. And the second entry here, this is for page 1, which is our code. The second page of our code can be found in frame number 3. And then the third page of our code can be found in frame 0. So the next two entries are for our data. So the first page of our data, which is in logical page 3, is found in frame 8 in our RAM. So again, to remove clutter in my diagram, I intentionally don't include the frame numbers for our heap, but these 3 gray boxes are supposed to be for the heap pages or the heap frames. So now let's look at how address translation is done by MMU Hardware. So again, to remove clutter, we will focus only on the 2 data pages starting at logical address 8000. In the page table, these 2 pages correspond to index 3 and 4 because page 3 and page 4, index 3 and index 4. And the first data page labeled data 0 in RAM is at address 8000, frame number 8, address 8000. And the second data page is at frame 1, address 1000. So now let's say your program is trying to fetch a data at logical offset 3100. So 3100 is somewhere in here. From the layout of the logical address space, you can see that logical address 3100 is physically 100 bytes from the beginning of the page. So that means the CPU will issue the address as a pair of page number 3, and offset 100, which corresponds to logical address 3100. When the MMU hardware receives this pair 3 and 100, it will do a lookup into the page table, use the page number as an index to the page table, and that number will tell the MMU where to find the data. So the data is in frame 8, but because the page size and the frame size are the same, so offset 100 in the page will correspond to offset 100 in the frame. So that's why when the address is translated from logical to physical, the offset 100 will be reused again, but the page number 3 will be replaced with frame number 8 based on the information we have on this table. So now this hardware will able to tell us that logical address 3100 corresponds to the physical address 8100. So what is important from this example? Apparently, when the page size is a power of some number, in our case 10 to the power of third, then automatically the last 3 digits, because the page size is 10 to the third, the last 3 digits of our logical address is automatically the offset in the page or offset in the frame. And then the remaining number before to the left of the offset will be either the page number or the frame number. So let's generalize this idea. So this example, we have a 7-digit address and see the effect of page size to the split up of page number and offset. So the top left table, so the address is a 7-digit address in base 10. If we pick the page size to be 10 to the power of 2, then automatically the last 2 digits of the address will be the offset. So here with this example, the page size is 10 to the second, then offset is 89. So when the page size is increased to 10 to the third, then the last 3 digits will be the offset. and then likewise for 10 to the 4 and so on and so forth. And with page size of 100, that means the offset ranges from 0 to 99. When the page size is 1000, the offset ranges from 0 to 999 and so on and so forth. So let's look at the second example. So here, when the page size is 8 to the power of 2, then the last two digits of the logical address are the offset. And when the page size is 8 to the third, the last three digits are the offset, and so on and so forth. Same thing with base 16. So this is an address in base 16, and with base 16, when the page size is 16 to the second, then the last two hex digits are the offset. And then when the page size is 16 to the third, the last three digits of the logical address are the offset. And with hex numbers, then the maximum offset is now FF, because the last two digits are the offset. The highest value for a hex digit will be F. So when the last two digits are the offset, then the maximum offset will be FF. So in general, when the page size is some number B to the dth power, so then the D digit, the last D digits of the address is the offset within a page or a frame. And of course, this math will work for any base, including binary base 2. So next, we want to look at the internal MMU hardware for paging. But let's refresh ourselves the design of MMU hardware for segmentation. So this is a diagram that you have seen before, and everything in the diagram has been grayed out except for the two components. So the first red components on the left side is the comparator. So why do we need the comparator in segmentation? Because we have to compare, we have to make sure that the offset in the logical address is not bigger than the segment size. So 153 is compared with the segment size of 400. If that number is smaller, you can continue to translate the address. If that number is bigger, then the MMU hardware will trigger an exception. And the second important unit in segmentation hardware is the addr, the arithmetic addr. And we have to add the offset 153 to the base address of the segment in order to get the actual physical location of your data or instruction. But later we will see that in paging, the comparator is not required, and also the addr is not required, because we don't have to add any number, because later you will see the adding operation, quote unquote, for paging is simply a bit padding operation. So this is a typical hardware design for paging. And again, we are using unrealistic example of page size 1000. 1000 is a nice example, although this is unrealistic because this is 10 to the power of 3. So we learned before, when the page size is 10 to the power of 3, then the last three digits of the logical address will be the offset. So assuming the logical address issued by the CPU is page 4 offset 230, so technically the logical address is 4230, and the MMU hardware will use the page number as an index to the page table. The entry at index 4 of the page table will tell us the frame number. So what happened here is the page number in the logical address will be replaced with the frame number looked up from the page table, and the offset will be reused again to generate the physical address. So this is the logical address here, and this is the physical address, and you can see from here we don't need to use comparator, and we don't have to add. So from here we see that the comparator is not required anymore, and we don't have to add, because practically what the MMU hardware is doing is to replace the page number 4 with the frame number. Again, that's why I call it like bit padding operation. We don't have to add. But as you remember with segmentation, there's an overhead in using the segment table. Likewise, that's the same for paging. For every memory references issued by the CPU, the hardware is actually doing 2 memory references. The first reference is to the page table to obtain the frame number, and the second reference, the second memory reference, is to fetch your data or instruction before that instruction or data can be returned back to the CPU. When working with memory address and large number of bits, it will be handy if you remember some important units for binary numbers. When we talk about salary to your future employer, you may say that your starting salary is 80K, which means 80,000. But remember, in computer science, 1K, 1 kilo, is not 1,000, but 1K is actually 1024, because this number must be a power of 2. And this table just to remind you the important units: kilo, mega, giga, tera, peta, and so on and so forth. And the next table, just a reminder for you to do number conversion, how to convert from decimal to binary to hex. And again, one important thing from this table is just remember, when converting from binary to hex or the other way around, always remember that 4 bits is equivalent to 1 single hex digit. So now let's use the 2 tables to do a quick arithmetic. So again, I assume you remember the units, the important units, kilo, mega, giga, and so on. But also I assume that you remember how to do multiplication when you see numbers with exponent. So here I have 2 to the power of 10 multiplied by 2 to the power of 8. And by the rule of multiplication for numbers with exponent, then you just add the 2 exponents together to get 2 to the 18. Remember, this is also useful when you try to break up a large number into its smaller constituents. So here I have 2 to the 34 on the left hand side, and if I break it up into smaller values, I will get 2 to the 4 and 2 to the 10 3 times. So then let's look at some examples below. So what you see in this table, the leftmost column is a number in hex, and we try to convert this number to decimal using binary units like kilo, mega, and so on. So the first example, the hex value is 10, and it will be easier if you convert that number to binary. So the left 1 converts to 0001, and then the right 0 converts to 4 zeros. And this number has 4 trailing zeros. That means the value of that binary number is actually 2 to the 4. So 2 to the 4, which is 16, because we have 4 trailing zeros here. The second example, the number is now in hex 100, and if you convert then again to binary, and you will see 8 trailing zeros, and that's why this number is equivalent to 2 to the power of 8, which is 256. And what if the first number is not a 1? Let's say that number is a 4. Again, if you convert this to binary, then the leftmost 4 will translate to 0100 followed by 8 zeros. But now if you look at the number of zeros, the number of trailing zeros, we have 10 of them. That's why the value of this number is 2 to the power of 10. but 2 to the 10 is a special unit, which is a kilo, 1 kilo. So I can now replace that number with 1k. So the next example highlighted in red is a bit trickier than the previous examples. So 3000 in hex, when you convert this to binary, you will see the 3 becomes 0011, and out of the last 3 zeros in hex, you will get 12 binary zeros. So then, what is the value of this number in decimal? Well, the 12 zeros here is now 2 to the power of 12. But in front of those 12 zeros, we have number 3. So technically, this is just a multiplication. So 3 times 2 to the power of 12. But I want to factor out 2 to the 12 because I see 2 to the 10 in here. So then 2 to the 10 becomes 1 kilo, but out of 2 to the 12, I can break it up into 2 to the power of 2 and 2 to the power of 10. So then all together, this is like 4, this is 1k. So the last two groups here are 4k. So 3 times 4k becomes 12k. The next number is easier to analyze. This is just 1 followed by 4 zeros. In binary, this is what you see, and you will see like 16 zeros in here. That means the value, the decimal value of that number is 2 to the power of 16. But again, because I see 1k in here, I want to break this up into 2 parts, 2 factors. 2 to the power of 6 multiplied by 2 to the power of 10. And 10 is 1k, and this is 64. So then the combined value is 64k. The next example should be easy. This is just 1 followed by 20 zeros, and 20 zeros is 1 meg. So the next example is again a trickier example, but again, if you expand this number into binary, this is what you get. So we have 1, 2, 3, 4, 5, 6 zeros in our hex number. So those 6 zeros becomes 24 zeros in binary, and the leading number is 5. So then if you rewrite the decimal value, this will be 5 times 2 to the power of 24, because 24 zeros. But again, I want to break up that big exponent into 2 parts. I can see this is like 2 to the power of 4 multiplied by 2 to the power of 20, but we know 2 to the power of 20 is 1 meg, so this number is essentially 16 meg. So 16 meg times 5 is 80 meg. So let's pause here for you to do some exercise. So the exercise asks you to express these numbers in hex. So let's now look at memory addresses expressed in hex. In particular, we will see the address as used by the MMU paging mechanism. Remember, we learned earlier that when the page size is b to the power of d, some base b, then the last digit, the last d digits of the address are the offset. But for this to work correctly, the address must be expressed in base b. So assume we have this 20-bit address DC93A in a system where the page number is a 4-bit number. So because total we have 20 bits, then the remaining 16 bits must be for the offset. But as we know earlier, the address, in order for this to work in bit, then the address must be expressed as a binary number. So the hex DC93A must be first converted to a binary number. So DC93A, so the first hex translate to 1101, and then the next hex to 1100, and so on and so forth. using the 4-bit as page and then 16-bit as offset. So now we can see that the first 4 bits will be the page number and the remaining 16 bits will be for the offset. It's very easy from here to see that the page number is D and the offset is just C93A. And because we have the offset in 16 bits, then the maximum offset must be when all these bits are ones, in which case we will see 1 1 1 1 all the way, so F F F F when we translate the number to hex. So what is the decimal value of this number? If we add 1 to this number, what we get is 10000 in hex. So 1 followed by 4 zeros in hex, which is 1 followed by 16 zeros in binary. So that's why we see 2 to the power of 16 minus 1. So with only 4 bits used for the page number, then the total pages would be just 2 to the power of 4. So we have 16 pages total from this system. Now with 20 bits total, that means the total addressable memory is 2 to the power of 20. But remember, 2 to the power of 20 is a special unit, so we have like 1 meg. So in this case, 2 to the power of 20 is equivalent to 2 to the power of 4 multiplied by 2 to the power of 16. Well, why am I using these two numbers? Well, because the page is encoded as a 4-bit value and the offset is encoded as 16-bit value. So that's why I'm using 2 to the power of 4 multiplied by 2 to the power of 16. So then practically we can see the system has a total of 16 pages and the size of each page is 64K, which is 2 to the power of 16. So now look at the same example again, but what if we change the page number and the offset to 5-bit for page number and 15 bits for offset? That means that the leftmost 1 from the C should belong to the page number, not to the offset. So then from here we can see that the page number is actually 11011, 11011. But remember that you have to group them in 4 bits starting from the rightmost bit, not from the leftmost. So that means the page number in hex becomes 1B. And then the offset will start from here. So the offset will start from 100 to the end. So this is the offset. And again, when I convert the offset to hex, that number is a 4. That number is a 9, this is a 3, this is an A. So the maximum offset is when we see all 1s for all these bits. If we have a 1 on those 3 bits, we're going to have a 7. So when we have all 1s on that group, we will see an F, same F and F here. So 7FFF, 7FFF. And if we add 1 to that number, what we're going to get is 1 followed by 15 zeros. So 1 followed by 15 zeros is 2 to the power of 15. And this number is very close to 32K. So how about the number of total pages? Because we have 5 bits for the page number, that means we can see at most 2 to the power of 5 or 32 pages. And the total memory is still the same, 2 to the power of 20, which is 1 meg. But this 1 meg is now the product of 2 to the power of 5 times 2 to the power of 15. So technically we have 32 pages and each page is 32K.